All right, so we have this unit. We're going to talk about electronic structure of atoms, but before we do that, we got to talk about light a little. Last time we talked, we said that ionization energy is the amount of energy required to kick an electron out of the atom. And when an electron leaves the atom, energy is released, and we see that energy in the form of light, which I'll show you actually in person in a little bit. So a couple characteristics of light that we talked about last time. We said that light always moves at a constant speed, 3 times 10 to the 8 meters per second. The variable for this is the letter C. Okay, and so this is one of the constants. Another characteristic of light is that the distance between each wave is called wavelength, and this is the unit of measurement here. We measure it in terms of meters, so nanometers, micrometers, things like that. And then we have frequency. We talked about this last time as well. This is basically how many waves you get per second, but usually the unit of measurement is just 1 over seconds. Also, seconds to the power of -1. You might also see it in terms of something called hertz. Okay, so this is what we kind of left off last class. So for the measurements with light, we have to do a lot of scientific notation. So just make sure that you are very comfortable doing it. We're going to do a lot of practice as we do it, obviously, but just a heads up about that. So if you have your calculators out, this would be a good time to take it out. We are going to practice that by doing a little practice problem with wavelength. So what I want you guys to do is I want you guys to convert 650 nanometers into meters. We got the conversion right here. So let's see how comfortable you are. I know it's been a while since we did scientific notation. So take about a minute or two, convert, and then we'll go over and then move on. All right, guys, so let's do this conversion. It's pretty simple. So we got 650 nanometers. We look at nanometers, and 1 nanometer is 10 to the -9 meters. So it's very simple. 650 nanometers, we can, gosh, I can't write. Nanometers is basically going to be equal 650 times 10 to the -9 meters. Okay, that's what this nanometers means. You're basically substituting this nanometers part with times 10 to the -9 meters. Okay. Now, we got to do it in scientific notation. To do that, we need only one number in front of the decimal. So what we have to do is we need to move the decimal twice to the left. Okay, so that's how we can get scientific notation. So we should get 6.5, but if we do that, we have to change the exponent. Okay, now if you move the decimal to the left, okay, the exponent, the exponent value, is going to go up. Okay, so it's 10 to the -9. So this is where a lot of students get tripped up because they see, oh, it's going to go up, and then they go to -10, -11. But if you look at it on the number scale, that's going down, right? So we're not talking about magnitude here. We're talking about the actual value of the number. So if we're going up, we actually need to go -8 and then -7. So this is going to be 6.5, excuse me, times 10 to the -7 meters. So if you want to write this little tip right here, you can. If you move the decimal to the left, exponent value goes up. If you move it to the right, obviously the opposite, the exponent is going to go down. And this is going to be talking about the actual value of the number, not the magnitude. So you have to look at whether it's a positive or negative sign. Okay, so that's the trickiest part. And as we do more of these calculations, you'll see more of these come up. A lot of students miss point because they do everything correctly, but just at the very end, they move the exponent the wrong direction. So just make sure you're careful about that. All right, so we talked about frequency already. Now, frequency, let me just reiterate, it's basically how many waves come per second. So exactly what it sounds like, frequency, how frequently the waves come. Okay, we see it typically when it comes to things like a radio station. So if you listen to the radio, radio waves are measured in terms of kilohertz. So you might hear that when they broadcast like what radio station they're on. And all of these characteristics of light, they are connected to one another, and this is the equation for that. C, so the speed of light is equal to the wavelength times the frequency. So this is our first equation. The speed of light, C, right? This is the 3 times 10 to the power of 8, is equal to the wavelength and then the frequency. All right, and this equation, what it basically shows us is that there's an inverse relationship between the wavelength and the frequency. And this, if you think about it logically, it makes a lot of sense. So I know we're talking about light waves, but let's think about the waves that we're most familiar with, right? We live in Long Beach, so we have the beach right there, so we can see the waves. So if you go out into the water, so let's say this, you're at the beach, right? This is you, okay, and you're in the water, okay? And then if you get hit by the waves, right, there's energy that it hits you with, right? Now, if you increase the wavelength, right, so let's say this is the wavelength, and obviously you don't need to draw this, but if the wavelength is increased, what's going to happen is the frequency of the waves is going to decrease, right? You're going to get hit by less waves per second, right? So if you increase the wavelength, that's going to result in a decrease in frequency. You're going to get hit by less waves frequently. But let's say you decrease the wavelength. So the waves start getting closer and closer together. Okay, what happens to the frequency? It's going to go up, right? And so that's the same thing with light. The wavelength, the distance between the waves, has an opposite relationship with the frequency. Okay, so just think about when you're on the beach, if the distance between the waves is shorter, there's going to be a higher frequency of those waves hitting you. And that's the same thing with light waves as well. Oh yeah, one other thing I do want to mention is that if you guys remember, C is 3 times 10 to the 8 meters per second, right? Wavelength, we measure it in like nanometers, micrometers, and whatnot. So you're going to have to convert wavelength to meters if you want to cancel that out. So if you want to make a quick note about that, you want to make sure you want to convert your wavelength into meters. And then your frequency, we usually measure it in terms of seconds to the power of -1, and so that's totally fine. You're not going to measure it in different times. Yes. 3 times 10 to the 8, correct. There you go. One day I'll write better for you. Okay, so that leads us into a very important diagram called the electromagnetic spectrum. So before you write anything down, let's just kind of look at it, and then we'll analyze it, and then we'll do some problems with it. Okay. So this is called the electromagnetic spectrum, and basically, let's start from the middle. The middle shows you all the different types of lights that we basically that we talk about. So this side right here is radio waves, microwaves, infrared, and then between infrared and ultraviolet, there's this very small section that we can see with our eyes, and this is visible light. Okay, and then we go to ultraviolet, X-rays, and gamma rays. Okay, so that's how you can kind of look at it. Now, a couple things I want to talk about is that on the right side right here, this is going to be the low energy wave. So these light waves have very, very low energy. Okay, and then the other side is very high energy. Okay, and that's why if you're in the sun for too long, right, you get hit by too many UV rays, you get sunburns. It's because they have high energy. But there's radio waves going around us all the time, and that doesn't really affect us. So that's the reason why there's a difference between these waves. So low energy and high energy. Now, there's a relationship between the energy and the wavelength. Okay, and so the low energy waves, they have a very long wavelength. Okay, so if you look at it, the number is 10 to the power of 3. So the distance between the waves, that's going to be 1,000. So there can be up to 1,000 meters or more between these radio waves. Okay. Whereas if you go to the high energy side, the high energy, this very small distance in the wavelength, right? It's 10 to the negative 11. Okay, this is also related to frequency, right? We said earlier, small wavelength means that you have a high frequency, and obviously if you have a long wavelength, you have very low frequency. Okay, now this kind of makes sense if you think about it, because light is made out of these particles called photons, right? And so if you have a very small wavelength, you have a very high frequency. So that means when it comes to things like gamma rays and X-rays, these photons are hitting you very, very, very quickly, right? There's a lot of them hitting you. So if you think about that, just kind of on a macro scale, it makes sense that they would be high energy, right? Because if you're getting hit by these particles constantly with a very high frequency, that's going to be a lot of energy that's transferred to you. Whereas if you're getting hit by them once in a while, that's not a lot of energy, right? So that's kind of a way you could think about the distinction between these different waves. Okay. All right, so let's get into our first problem that has to do with this. If you have this chart up on your screen, that might be helpful. Okay, but I want you guys to use just the equations and the graph up there to answer 7, 2, and 3. First one, you're looking for the frequency of light that has a wavelength of 10 micrometers, and then frequency 5.5 times 10 to the 14 waves per second, and you got to determine what light it is. You're going to be using that equation we just talked about. Speed of light is the wavelength times the frequency. So go ahead, try that out. You'll use this in conjunction with the chart up here, and then we'll go over in about 3-4 minutes. Okay, guys, so let's talk about how we set it up. So we're going to use the C equation, and since we are looking for frequency in 7.2, we just need to rearrange it to solve for frequency. So it'll be speed of light divided by the wavelength. So 3 times 10 to the 8 meters per second divided by the wavelength. It tells us that the wavelength is 10 micrometers. And so I put micrometers here just for the setup, but you can just replace this with times 10 to the power of negative 6 meters, well, just meters. Okay, so you're just replacing micrometers with the conversion factor. All right, now, if you take a look, we can cancel out the meters, and the only unit of measurement we'll have left is per second, right, which is what we want for frequency. So our unit of measurement for our final answer will be seconds to the power of negative 1. Okay. All right, so we are going to do our math for this. So if you guys have a nice graphing calculator, it will just do it for you. But if you don't, I'll show you guys how to do the actual calculation. Now, if you look, it's division, right? So what we're going to do first is we're just going to divide the normal numbers. So 3 divided by 10. If you do 3 divided by 10, that'll give you 0.3. Okay? And then for the exponent, since we are dividing, what you want to do is you want to subtract the exponents. Okay, so 8 minus negative 6. That's the same thing as adding, so you'll get 10 to the power of 14. So if your calculator is not the ones you can plug in the graphing calculator, I know we're not done yet. You'll do 3 divided by 10, that's 0.3, and then you take the exponents, and then you just subtract them. 8 minus negative 6, that's why you get 14. Okay. All right, but this is not scientific notation, so we need to move the decimal 1 time to the right. Okay. If you move the decimal 1 time to the right, it's going to be 3.
10 to 13.
Correct. And then the exponent goes down to 13, and it'll be seconds negative 1. So this is going to be your answer. So again, the scientific notation might be the part that's a little bit tricky, might trip you up. But just make sure that you're comfortable with the scientific notation rules. Okay, let's go on to the next one. Next one is this right here. For this one, we don't need to do any conversions because we just have meters already, so these cancel out. And then you should get, for your final answer, 5.45 times 10 to the negative 7 meters. Okay, same rules for the calculations. All right, everybody good with the conversions? Or sorry, the calculations, my bad. All right, now we just need to figure out what type of light each of these values give us. So let's go to the first one, 10 to the power, or sorry, 3 times 10 to the 13 per second. So that's frequency. So we're gonna go to the spectrum and look for that. So we're looking at frequency, we're looking right here. 3 times 10 to the 13 is gonna be around here, 10 times to the 13th. So for 7.2, you should get infrared light. Okay, so just make sure you're careful which scale you're looking at because it's going to give you different answers. For number 3, the wavelength, it's in meters. So we're going to look for 10 to the negative 7, and that's going to give you ultraviolet light. Okay, so the first one is infrared, and the second one is going to be UV. So that's the type of questions you'll see in terms of wavelength, electromagnetic spectrum, so on and so forth. Okay, so before we go into talking about light and stuff and doing calculations, we're going to talk a little bit briefly about the structure of an atom. So we know that atoms are made out of protons, neutrons, electrons. You guys don't need to write this. You guys should know it. Protons, neutrons are in the middle in this place called the nucleus. That's the center of the atom. And then we got the electrons that are flying around. Okay, now, the electrons fly around. They're not locked into these nice orbits that we draw. This is called a shell model. And basically what this does is it tells us the areas the electrons are most likely to be. So electrons move around the atom, and they can occupy spaces between these shells, but they like to hang out in these areas, so these distances from the nucleus. And that's why we draw shells. It just shows us where the electrons are most likely to be. It's also just a nice way to draw it, and it's easy to visualize. But the key thing is that these shells are not real. They're not really locked into these orbits. This is just a mathematical representation to show where electrons are most likely to be. Okay. All right, so we're going to learn how to draw these shell models, though, because it does help us visualize these things. So it's very simple. If you guys have your periodic table, take out your periodic table. I'm going to go through it very briefly, but there are a couple of rules that we need to know for drawing these shell models. Okay. And I think it's easiest to learn just by drawing them. So we're going to start with a couple examples. Okay, so we're going to start with 7.4, and we're going to draw helium together. Okay, so right number 4, helium. All right, so let's look at helium right here. Helium is right here. Now, the first rule for drawing these shell models is super easy. Basically, the number of, or the row that the element is in, so the row number, that's going to equal the number of shells that element has. Okay, so whatever row it's in, that's how many shells it's going to have. So helium, if you look, is in the first row, so helium is going to have 1 shell. Very easy. If you look at something like aluminum, aluminum's in the 3rd row, so it has 3 shells. If you look at something like barium, barium is in the 6th row, so it's going to have 6 shells. Okay, very simple. All right, next thing we're going to do is talk about the electron. So we're talking about a neutral atom right now. See, so the electrons is basically just whatever the atomic number is. So helium has an atomic number of 2, so we just draw 2 electrons. It only has 1 shell, so that's the only place they can go. So that's how you draw helium. So if it's only 1 shell, like helium and hydrogen, you just put them all in the first shell. All right, but let's look at something a little bit more complicated. So we're going to draw carbon. Let me give you guys 30 seconds. See if you can draw the shells for carbon. How many shells carbon has? Should be pretty quick. All right, guys. So if you guys find carbon, carbon is right here. How many shells does it have? 2. It's in the 2nd row, so it has 2 shells. Great. Okay, so 2 shells. All right, now, if we look at carbon, it has the atomic number 6, so we need to draw 6 electrons. But now that there's 2 shells, we need to figure out how many electrons are in each shell. And this is where the next rule comes into play. The easiest way to think about this is you just basically count to the element, okay? I'll talk about what that means in a second, but you're going to count to the element, and the number of boxes that are in the row is equal to the maximum number of electrons in that shell. Okay, so I'll explain that in a sec, but we're going to count until we get to our element. So 1, 2, 3, 4, 5, 6. And the number of boxes that are in each row is going to tell you how many electrons go in that shell. Okay? So we just said that the rows represent the shells, right? So the first row represents the first shell. How many boxes are in the first row? 2, yeah, 1, 2. Since there are 2 boxes in the first row, that's the maximum number of electrons that can go in that first shell. So 2 electrons in the first shell. Since there are 2 boxes, that's the max. Next thing we're going to do is we're going to count to carbon, right? And so if we look at the 2nd row, how many boxes till we get to carbon? 1, 2, 3, 4. So that means there's going to be 4 electrons in the second row. And if you notice, 2 plus 4 is 6. That's how many electrons carbon needs. Super simple. Yes. Correct. So second row can hold 8, but we don't have enough to fill it up. So yeah, we just stop at 4. Great question. Alrighty. So that is the easy ones. Let me give you guys one that's a little bit trickier now. I want you guys to see if you can draw the shell model for F minus. F minus. The grade you're going to get in this class. Alright guys, let's go over number 6. So first thing we're going to do is figure out the number of shells. Okay, if you take a look at F minus, F is right here, second row, so it's going to have 2 shells. Okay, that part's pretty easy, right? Okay, now before we start drawing the electrons, let's talk about what that minus means. We said that the minus sign means that there are more electrons than protons, right? So if we take a look at F, F has 9 protons. That number is never going to change. But how many electrons does F minus have? 10. Yeah, it's going to have 10 electrons because the minus charge means that there's 1 more electron than proton. So it's going to be 10 electrons. So we got to draw 10 electrons in our picture. So same rules from here. The first row has 2 boxes, so 2 electrons in the first shell. And then we're going to have to draw the remaining electrons. So we drew 2 of them. That means we have 8 left. So that means F minus is going to have 8 valence electrons. 8 electrons in the final shell.
What if you did like any minus
Okay, so for Be2+, typically if we look at Be right here, it's going to have 2 shells, right? So don't draw this yet. I'll explain. We're going to draw 2 shells typically. Okay, but before we do that, let's take a look at Be and look at the charge. So if you take a look at the charge, it's 2+, right? So Be typically has 4 electrons. But if the charge is 2+, how many electrons does Be2+ have? It only has 2, exactly. So let's draw our electrons. The first row has 2 boxes. So you're going to draw 2, and then we have no more electrons, right? So if we have no more electrons, nothing can go in the second shell. So Be2+ is going to lose that second shell. It only has 1 shell. Okay, so that is kind of the trick for these cations. So if you want to make a quick note for yourself, the cations typically are going to have, they're going to lose their valence shell. Valence means outermost. So Be should have 2 shells, but if it loses 2 electrons, it's going to lose that second shell. And then if you look at number 6 for F minus, the anions, they are going to fill up their valence shell. Okay, so it fills up. And this actually shows us why the most common ions that we learned about are the most common ions that they are. F's most common ion is -1, right? And it's because it wants to fill up its valence shell to max it out. Be's most common ion is 2+, because it wants to lose the 2 electrons to max out, to have a completely full valence shell. So that's the chemistry behind why that pattern is what it is. Okay, so let's get into the next part. So that's the shell model. Now that we understand what these atoms look like, let's add in the light stuff to it. Okay, so we're going to talk about something called quantized energy. Quantized energy. Okay. Now, before we talk about quantized energy, I want you guys to write this equation down. Okay, and then I'll explain what quantized energy is. But this is an equation that we use to talk about quantized energy. Okay, guys, so let's talk about what quantized energy is, and I'll explain how it relates to this equation right here. So, quantized energy, very simply put, is basically saying that in an atom, the electrons have a certain amount of energy. Okay, so let me draw you guys an amazing, beautiful picture real quick. Okay, so we have an atom, and we have the nucleus, which is positively charged, right? And we have these shells that we just talked about. So let's say that we have an atom with 3 shells. Okay, now, if we have an electron in a shell, this electron right here has a certain amount of energy, okay? And this electron right here, because in the second shell, it has a different but also certain amount of energy. Okay, so we'll call it E1, E2, and E3 just to show that they have energy but different amounts based on what shell they have. Make sense? Okay, now, what quantized energy means is that in an atom, an electron will have very set values of energy. Okay, and it can only have those set values of energy. So let's say, for example, this amount of energy right here is, let's just give it an arbitrary number. Let's say it's 10. Let's say that this is 20 and this is 30. Okay, what quantized energy means is that electrons in this atom can only have 10, 20, or 30 for their energy. You can't have energy in between, like you cannot have 15, you cannot have 25. So you cannot have energy values in between these very specific values. That's what quantized energy means. It just means you are locked into very specific amounts of energy. Okay, an easy, I guess, real world example is, let's say that you are going up a staircase. Okay, right? When you are going up a staircase, you're going to have a certain amount of potential energy, right? Depending how high on the staircase you are. So let's say that you're on the second step right here. You have more potential energy than if you're at the bottom, right? Because if you're at the bottom, you have 0. Because if you fall, I guess it'll hurt still, but you can't really fall because you're at a very low distance. But if you're on the second floor, you can drop and hit the ground with a very specific amount of energy. But you can't have like 1.5 steps of energy because you can't step in between a step, right? So again, you're locked in to these energy levels, and that's what quantized energy is. These electrons also have quantized energy. You can't exist in between these shells. That's what quantized energy means. Now, how does this equation come into play? This equation basically tells us what is the energy that a photon can have. Okay, so this is a simplified equation, but this is the expanded one right here. Let me pull up your AP equation sheet just to make sure what you guys have. So if you look at your AP equation sheet, you have this right here. Okay, this is the one that you wrote down. However, what we can do is we can expand this equation for frequency. You have frequency right here. So if you want to expand it, and for a lot of questions you will have to expand it, frequency can be expanded to c over wavelength. Okay, so just keep that in mind. Okay, that's what the longer equation right here is telling you. It's basically taking the two equations from your equation sheet and you're basically combining them together, and that's how you get this third equation right here. Okay, and this allows us to figure out how much energy a photon can have. Okay, how much energy the light can have. We're going to use this H value. This H value is called Planck's constant, and it's provided for you. It's this very ugly scientific notation number. That's a constant, so it'll always be the same. And then it's the frequency of light. Okay. Okay, so let's use that equation. I just want to do a calculation with you guys using that equation, and then after that, I'm going to talk about how we can talk about quantized energy in the atom. But take a second, try solving 7.8. Okay, guys, so hopefully you guys got the calculations are good for you guys. Now, last thing we're going to do is we're going to figure out which which radio station requires or contains more energy. If you take a look at it, first thing you want to do is just look at the exponents because that's the most important thing. 10 to the negative 28 and 10 to the negative 26. Now, we talked about this earlier, but this is where, again, a lot of students can get tripped up because they see 28 and they say, oh, that's a bigger value, right? However, if you look at the exponents, it's negative 28 versus negative 26. So the FM is actually going to have more energy, and it's because negative 26 is bigger than negative 28. Okay, 28 has a bigger magnitude, but we're on the numeric scale, so negative 26 is a bigger number than 28. So that way, that's how we can figure out the FM radio station releases more energy with its broadcast. Okay, so let's talk about how this works with an atom. So basically, if we have, let's say that we have an atom, so we're going to get hydrogen, okay? Hydrogen has one electron, and it's in the first shell, right? Another way that we could think about shells is we also call these shells energy levels, okay? Because it's another way of talking about what's happening. They're a certain distance from the nucleus, which means they have a certain amount of energy. Now, we talked about how the atom can have multiple shells, right? Now, hydrogen, even though it has one electron and one shell, it can actually move up to different energy levels depending how much energy you put into it. So let's say that I put energy into hydrogen. Okay, so this is energy. Depending on the amount of energy, the electron can go up to the second energy level, the third, the fourth. There's actually even more energy levels beyond that. So you can put energy into an atom, and the electron can go up to different energy levels. But when it does that, what happens is that because it's at a higher energy level, the electron is unstable. So what happens is the electron will always drop back down to its normal energy level. And when the energy drops back down, what goes in has to come back out. And so it's going to release energy, and it's going to release energy in the form of light. Okay, and so this is how we can talk about quantized energy in terms of an atom. The electron can only go to these quantized levels. It can't go to level like 2.5. It has to go to level 2 or level 3. And once it gets there and drops back down, it's going to release a certain amount of light. Now, we said that depending on the energy the light has, it's going to have a very specific wavelength or frequency, right? And so we can actually visualize that through something called an emission spectrum. So if you put energy into an element, the electron will shoot up to a different energy level, and it will drop back down depending how much energy it absorbed. And we can tell how much energy was absorbed based on the color of the light that it gives off. Okay, so we just talked about how at different energy levels, an electron is going to have a different amount of energy, right? And we can see that based on when it drops, how much energy it releases. There's an equation that it's not on the AP test anymore, so you guys don't need to memorize this equation. But basically, so if you look, this is the only equation you need to know for atomic structure, but it might be on your homework or on the smart work, so I wanted to go over it very briefly. This equation right here, you don't need to memorize it, don't need to write it down even. I just wanted to let you know that this is an equation that we can use to figure out how much energy an electron has at a specific energy level. So for example, let's say that we're looking at an electron at energy level 3, third shell, okay? The energy that this electron would have is equal to negative RH, and this is a constant. And then you do 1 over n squared. N is the value of the energy level. So if on the third level, you do 3 squared. You calculate this out. That tells you how much energy is at this specific energy level. Okay, again, probably not going to be on the AP test. And if it is, this equation will be provided for you. But I just want to show you guys how to use this equation. Yeah. No, this will not be on your exam. I'm just letting you know. It might be on your homework, might be on the smart work, or some practice stuff you do. And if they do give you the equation, then I just want to make sure you guys know how to use it. But you guys don't need to memorize this equation. But this N is just going to be the energy level. So if we're looking at something at energy level 1, you would just do 1 squared. N is just the energy level. Okay. All right. With that being said, this equation can also be used to calculate how much energy is released when an electron drops from one level to another. So for example, let's say that we have an electron like in this picture where you drop from 3 to 2. Okay, so the n level is 3 to 2. Okay, if you drop in energy levels, basically all you would do is this equation right here, plug in 3 minus the same thing, negative RH 1 over 2 squared. Okay, so if you're doing change of energy, just do the energy that you start with minus the energy that you end with. Again, you don't need to memorize it. It's not on your exam. I just wanted to let you guys know how you can use this equation to calculate how much energy an electron has at certain energy levels. Okay? If you're going to punt on something, this is something you can absolutely punt on. Okay? You can just ignore this, but if it comes on your homework, just this is how you do it. Okay, let's move on. So we're going to talk about something called electron configuration now. And electron configuration is a way that we can describe where the electrons are in an atom. Okay. So when you look at a shell model, okay, we talked about how the shell model has shells, right? So we talked about shells. These are the energy levels. However, there are these things within the shell called subshells. Okay. And subshells are basically regions within the shell that the electrons can be in. So they're regions within the region. Okay? So they're regions within the region. It does get a little bit more detailed than this, and if you guys are all doing your reading, right?
Of course.
Yeah, if you guys are all doing your reading, you guys will see the details of this, but I'm going to show you guys what you need to know for the actual problems that you're going to be doing, okay? So using this information about shells and subshells, you can actually assign these things to elements called quantum numbers. Okay, so just jot this down somewhere. And quantum numbers basically is telling you how many electrons an element has, and also where those electrons are. That's basically what it is. And there's a couple different ways these things, this topic comes up in problems. So we're going to talk about the different types of problems that you're going to see. The first thing we do with these quantum numbers is we write something called an element's electron configuration. So I'm actually going to bring up a blank screen real quick. And the first thing we're going to learn how to do is something called electron configuration. So electron configuration. Okay, and when we write an element's electron configuration, basically what we are writing is we are writing how many electrons it has, and also the shells and the subshells that the electrons are located in. Okay. So we're gonna do some examples on the periodic table real quick, and that should help you kind of figure out how to do this. It's actually pretty simple. Okay. So let's take a look at our periodic table, and there's these different regions that we're gonna look at. So the first subshell is called the S subshell. Okay, and I'm going to do it in red, S subshell. Okay, and these are the sections on the periodic table that the S subshells are in. So it's going to be basically these first two columns. Everybody in this first two columns are going to be the S subshell. However, we also include helium in there. Helium is part of the S subshell. And if this is kind of confusing, don't worry. It'll make more sense as we do the problems. Okay, everybody on this right side, okay, right here, this is called the P subshell. Oops, sorry, not S shell, S subshell. My fault. All right, guys, let's go over carbon. So if you look at carbon, same thing as before. We're gonna write down all the electrons underneath carbon because it still has those. So carbon is gonna have 1s2, 2s2 because it has these ones right here. But carbon is in the p section, the 2p section. So we're gonna write 2p. How many does it have in the 2p? It has 2. So it'll be 2p2. Easy peasy? Okay. Let me give you 30 more seconds. See if you guys can do, we're going to skip up a little. I want you guys to do F. Okay, see if you can write the electron configuration for F. All right, guys. So fluorine, again, do the ones underneath it first. It has 2 in 1s, so 1s2. It has 2 in 2s, so 2s2. It's in the p section, 2p, so 1, 2, 3, 4, 5. So it'll be 2p5. All right, we're gonna do 2 last ones, and then we'll finish up. Let's do Mg. I'll do Mg with you guys, and then I'll have you guys try the last one on your own. And if you feel comfortable, you can just ignore me and just do it on your own. Just check your answer. Okay, Mg is right here. And we got to do everything underneath it. So 1s is 2, so we're going to write 1s2. It has 2 in 2s1, or sorry, 2s, so 2s2. It has 1, 2, 3, 4, 5, 6 in 2p, so that's 2p6. It's in the third row, so it's 3. This is the s section, so 3s1, 2. So it'll be this right here. All right, last one. I'll have you guys do this on your own. We'll go over and we'll finish up for today. I want you guys to do P, do phosphorus. All right, guys, let's go over the last one. Same thing as before. Always do the electrons under it first. So we got 2, again, in the 1s section. So 1s2. You have 2 in 2s, so 2s2. You have 1, 2, 3, 4, 5, 6 in 2p, so 2p6. You have 1, 2 in 3s, so 3s2. And then lastly, p is 1, 2, 3 in 3p, so 3p3. And that's going to be electron configuration.